Спасибо. I think I should speak in English. Yes? Yeah. So thank you. The title of my talk is Generalizations of Casey theorem for higher dimensions. First, I would like to thank the organizers, especially Nastya and Dasha, for such a nice conference. It is well organized indeed. And it's a pleasure for me to give a talk here. All we know the ancient Ptolemy's theorem. It says that arbitrary quadrilateral on Euclidean plane can be inscribed in a circle if and only if the sum of products of the opposite sides of this quadrilateral is equal to the product of its diagonals. The modern formulation of this is called as Ptolemy's inequality, and states that for any 4 points on a plane, the following inequality holds. And the equality is attained here if and only if these 4 points in prescribed order laying on some circle. There is a direct generalization of this result. So at the end of 19th century, Irish mathematician John Casey proved this theorem. So let 4 circles on a plane, again on a Euclidean plane, touch given circle O. They can do that, for example, as shown here. So all 4 small circles sitting inside of the big circle, or like here, or anyway. So then we denote by Tij the length of common tangents between the circles OI and OJ. And so if these 4 circles touch some common circle, then for the length of common tangents, this equality holds. But we should be accurate. So if, for example, circles O1 and O4 are sitting both inside of the circle O, then we should take the external common tangent, T14. But else, if the circle O separates these 2 circles, then we should take the internal common tangent. What means external tangent and internal tangent? So 2 circles. This is the external common tangent. Again, the same circles. And this is internal common tangent.
Can these circles intersect?
Yes.
Okay.
This is a well-known theorem nowadays, and usually some speakers say that this is a Casey theorem. But 1881. But much later, the converse to this direct Casey theorem was proved by different authors with different kind of restrictions. So one of them belongs to Bakker. So here is a converse Casey theorem. In some sense, it's more difficult. It's more difficult to prove, and it is more useful for applications. So given just the 4 circles on the plane, denote by Tij the lengths of common tangents for any pair of these circles, of these four circles. Then if one of three quantities, one of three real numbers, one of three products of these six common tangents is equal to the sum of other two, then these four circles touch a common circle or a common straight line. So direct Casey theorem was proved in 1881. Converse theorem is in the middle of 20th centuries. And as I said, together direct and converse Casey theorems gives us a criterion when four circles on a Euclidean plane touch a common circle or a common line on a Euclidean plane. So together they generalize a Ptolemy theorem, a Ptolemy inequality. And all above mentioned, and for example, in the case when we consider not four circles but just three, we have a Apollonius problem. So all the above mentioned metric theorems have exceptionally, how to say, they are very natural and general. So they have place not only in Euclidean geometry, but in non-Euclidean also. So first, in the book of Darboux and Frobenius, they found a spherical version for Ptolemy's theorem. Then a Ptolemy's theorem on Lobachevsky plane was independently found by Kubota, Shirokov from Kazan University, and Valentine. I think Valentine is a former Coxeter student. And for the Casey theorem, the direct Casey theorem on Lobachevsky plane and on the sphere was given in our joint work with my student Luda Mikhailova. And then Kostin and Kostina gives interesting interpretations of Euclidean and hyperbolic Casey theorem. But today I will try to show you Euclidean generalization of direct and converse Casey theorem for higher dimensions. That is our joint work with Vladislav Aseev. And to do this, I need to introduce a few notions. So first of all, we will consider generalized, instead of circles, lines, and so on, we will consider generalized n-dimensional balls. That is a closed subset of Rn completed with infinity, and that is just one of four situations. It is a Euclidean ball, or it is a complement of Euclidean ball, or it is a half space, or just one point. So all situations are possible for generalized ball. In all these cases, a generalized ball can be presented as an inequality of this type. Here, coefficients alpha and beta are just real numbers, and parameter A is an n-dimensional vector. Thus, any generalized ball can be encoded with a coefficient vector alpha, A, and beta. This coefficient vector has a dimension n plus 2, and defined up to multiplication by a positive number. And we introduce the following bilinear form in the space of these coefficient vectors of generalized and balls. Here just a scalar product of n vectors a1 and a2, Euclidean scalar product, and minus some real number. By definition, this form Q has these properties. So for the same ball, B given by its coefficient vector L, QLL is equal to 0 if and only if B is just 1 point. So that's good. Now let me introduce a new quantity. We called it psi characteristic of two generalized balls equipped with labels, with unit vectors which have a dimension n-1. I will explain the meaning of these labels, of these vectors, E1, E2, a little bit later. So, psi characteristic of two labeled generalized balls is just scalar product of labels minus this quantity. So here Q is a Q form defined on the previous slide, and L1, L2 are the coefficient vectors corresponding to balls B1 and B2. And this quantity has a useful property. This property, we use this property to prove the theorems. It is invariant under Möbius transformation of the space. And why we actually need this quantity, why we choose this psi characteristic? Because we can use it to define the generalization of notion tangency. You know that in the plane we have just two possibilities. If we have one circle touching another circle, so there are just two possibilities, one and the second one. So one circle can touch another from two possible sides. But if we go to three-dimensional space, so for example we have a circle again in three-dimensional space, which is a circle which is a one-dimensional sphere, and it touches a three-dimensional ball, and we fix the tangent point, then we have infinitely many possibilities. So we can rotate this ball around this circle, around this tangent point. And to control this situation, we need labels. And in the most general case, when we have n-dimensional balls and k-dimensional spheres, that is enough to have n-1 dimensional unit vectors to control the situation completely. Even n minus k dimensional unit vectors are enough. And here is the formal definition of generalized notion of tangency. So let non-one-point generalized balls Bj are equipped with labels with unit vectors Ej. Then we say that some generalized k-dimensional sphere S is called psi-tangent k-sphere to the number of these labeled balls if this condition holds, if this equation holds for any I and j indices. Geometrically, this means that S, here is S, touches each ball, Bj, in such a way that unit label vector Ej lying in orthogonal complement to the k-sphere S at the point, at the tangent point, will direct it exactly to the center of this ball, Bj. Okay. So now we have, I think, everything to formulate the result. So let k-dimensional, first of all, direct Casey. Let k-dimensional generalized sphere is psi-tangent k-sphere to 4 labeled non-one-point generalized balls. Then 3 conditions hold. First of all, the psi characteristic for any pair of these 4 balls should be non-negative, and the equality to 0 is attained here only in a few special situations, like one ball is lying on the surface of another ball or something like that. The second condition is the main one. For any renumbering of the balls, this inequality holds. This is a generalization of Casey inequality, or, if you like, Ptolemy inequality. And the third condition says when the equality is attained in this generalized Casey inequality. So when the equality is here, the third condition describes when. That is a direct Casey theorem, and here is a converse Casey theorem. So let non-one-point Euclidean balls with labels, here just plus or minus 1, satisfy the following conditions. First condition, psi characteristic of any pair of labeled balls, of these labeled balls, are non-negative. And the second condition, for any renumeration of balls, this generalized Casey inequality holds. Here the lengths of common tangents. And the last 2 conditions are just to exclude some degenerated cases when there is no possibility to, when there is no common common k-sphere psi-tangent for these 4 generalized labeled balls. So if these conditions holds, if they are true, then there is a common k-dimensional sphere which is psi-tangent to these 4 generalized labeled balls. So that's it. And sorry, and some another condition, another theorem, when we consider not 4 but 3 balls, 3 generalized balls, and 1 more point. which is not in the unit of these three balls. Then we can formulate the same theorem, the previous direct and converse theorem, just in one statement. So here is a criterion when psi tangent cosphere to three labeled balls passing through the given point is exist. So it is exist if and only if this three simple condition holds. And that is some of possible, that is one of possible generalizations of Apollonius problem. Not only one, but just one. So thank you for your attention.
There are some questions.
What is the main point of proof?
I think the main point of proof is so you already saw some machinery. I mean, we introduced a special notion of psi tangent and of psi characteristic, which is invariant under Möbius transformation. So the main point we find such a Möbius transformation when this cosphere became just a plane, hyperplane, k-dimensional hyperplane. And in this case, we can collapse the smallest of four balls and use the last theorem for Apollonius. And then we do the same for the second and so on. And at the final step, we use just Ptolemy inequality.
With some kind of
Reduction. Yes.
In dimension.
Yes, but yes. You're right.
Some other?
In classical cases theorem, we have inequality or equality?
I think usually, so the only theorem which is well known here is the first direct Casey theorem. Usually, if you find some book for students, for pupils in the school, some popular book, you can find just this direct Casey theorem, which says when the equality holds, which says if this geometrical situation is presented, then this equality holds. Just this. But yeah.
But Casey's theorem is generalized Ptolemy theorem.
Yes.
But in Ptolemy theorem we have inequality.
You are right.
And
we cannot
go to limited case and then get in Ptolemy theorem equality.
You're right, I understand you. So, here is a modern formulation of Ptolemy inequality. This is a criterion, yes? So, for any 4 points, the inequality holds. And equality here is attained if and only if. So if we combine direct Casey theorem, which is classical, and converse Casey theorem, which is not so very well known, then we again have a criterion.
Generalized of Ptolemy theorem is direct Casey theorem plus
converse. Then we have if if the equality holds, then we have this geometric situation. Or if this geometric situation is presented, then this equality holds. But for inequality, it is not true. It is not always just, how to say, it depends of renumbering of spheres.
Okay. Yeah. Okay.
In Möbius case, you have a ball and complement ball, so they are the same. But if you have 1 point ball, if there are some complement ball to 1 point ball, some kind of infinite ball.
No, we consider just the closed balls as a generalized
But
balls.
possibly all the space is complement ball of 1 point ball.
But it should be complemented by infinity to be closed.
Yes, in Möbius case it's the same here, but you don't look at this kind of balls.
Yes, we look at only at closed balls.
Okay. So, maybe we discuss.
Ну, примерно понятно. То есть зачем это надо? Почему не получается?
Да.
Нет, да там нет бесконечного. Вот я и спрашивал, как бы сказать, напрашиваться.
Они не хотят.
Да, нет. Вот вопрос, почему нет. Ну, я согласился.
Я равно нулю, альфа, бета равно нулю, положить. Годится, да, альфа, бета равно нулю. Да, все получится.
So let us send speaker again.